So today we're continuing our lessons on optimization. We're doing this pair of problems that are very, very common. You're very likely to get one or both of them on the test. The Lighthouse question and then the train question. So what I'm going to do here is I'm going to do Lighthouse question number 1. I'm going to leave you number 2. I'm going to make a discussion post in the discussion area. I want someone to solve it. I want you to discuss it with each other and see if you can do it. You can imagine what I usually do today is I use the boards and have you uh, solve it in groups and stuff so you can discuss it with one another, but that isn't really an option at the moment. So let's let's do number 1 together. You can do number 2 on the website, and then I'll cover this train problem as well. So let's try and put the information from this question, just deal with it piece by piece here. So it says a lighthouse L is located on a small island 4 kilometers west of point A on a straight north-south coastline. All right, so let's go to here. Okay, let's delete the I don't really have that option. Okay, so let's draw x equals 0. So here's our coastline. Okay, and then let's draw an inequality x greater than 0, and we'll call this we'll make this green for it being the land, and then we'll go x less than 0, and that'll be the water. Okay, so there's our water's over here, our land is over here. We have a straight north-south coastline, and then we have a lighthouse L is located on a small island 4 kilometers west of point A. Okay, so let's make point A, we'll just say A is located at 0, 0, and therefore L is located at -4, 0, right? So 4 kilometers west of the coastline. Okay, now, all right, so this is what we know so far. A power cable is to be laid from L to the nearest source of power at point B on the shoreline, which is 12 kilometers north of point A. So point B is going to be located at 0, 12, right? So 12 kilometers north. So there's point B up there. All right, let's just, so we can make this a little easier to see. Oh, I see. Sorry, just wanted to get rid of the just get rid of the numbers here. Make this a little easier to visualize. All right, so this is what we've got, right? And in fact, why don't I just get rid of the x-axis? Just realized we don't need an x-axis here. I guess it doesn't hurt. Okay, sorry. So point B is up there, 12 kilometers north. Point A is here, and then the lighthouse is here. Now, the goal in the question is to create a power line, okay, from point B to point L. So that's all you had to do. Create a power line from B to L, okay? Except the cost of laying the cable underwater is $6,000 per kilometer, and the cost of laying cable along the shoreline is $2,000 per kilometer. So how should you how should you build your power line here so as to minimize the cost? Obviously, so let's make a new point C. Okay, so point C will be the amount that we sort of put the power on the land. So let's draw a segment from B to C, and then a segment from C to L. Okay, and let's change the color of this just to make it a little easier. So we'll make it very, very thick. And there's our power line. Okay, it runs along the coastline until it gets to C, and then across the water to get to L. Now, of course, if you just drew directly to B, that would be very efficient from the point of view of distance, but it's probably not going to be very efficient from the point of view of cost, because running the cable underwater, right, is way more expensive than running it on land. So what we have, we have on the other hand, if we go all the way down here, we've run the entire cable along the ground and then some of it across the water. Now the cost of running the cable, right? So the cost. Oh, interesting. That's a function. I didn't know that. Cos t, I guess, is a function. All right, anyway, so cost of the equation is going to be whatever our length of line segment f is. So on ground it was 2,000, so we'll put it in thousands. We'll go 2f plus 6g, okay, would be the cost. So if I were to make the equation exactly the way you see it now, it would cost me 50,000 to build, right? Let's make a quick observation here, which is we'll make f and then cost over 10. So watch what happens to the cost as I change the dimensions that I use. If I go all the way down here versus if I go all the way up here, right? My cost is quite a bit higher if I just go directly through the water. My cost goes lower, 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 lower. It's like it's getting better and better and better and better. And then somewhere around this point, somewhere in this area, is the right answer, right? Where my cost is at the absolute lowest. If I go any closer to A, my cost actually starts to rise again. And it should be obvious that if I go past A, I'm just wasting cable and you know, my cost is not going to be optimized. And similarly, if I go past B and then come back, you know, that also is going to be nonsensical. It's not going to give me an answer that makes any sense. So I'm looking for an answer somewhere in this region where I could design the ideal spot to lay the power line. Okay. So what we need to do here is we need to think about where point C is, and then how long segment G is versus how long segment F is. Okay? So that's what we're doing. So let's go back for a sec. Let's eliminate the two segments for a minute and eliminate this thing. You can see that the variable, the only thing I'm controlling, is C, which we'll think of C as the y distance, right? Or the amount of cable that's laid along the land. Just get rid of this so we're not distracted by this for a sec. The only variable I'm changing is C. So what I'm going to suggest is, let's create a segment, AC, and we're going to call this segment L. Okay? And this L is what I'm going to use as a variable. Everything in my question I'm going to express by using L. And L is going to be the amount of land that is not actually part of my answer. And I know that might seem strange. It might make more sense to make L connected from B to C. But I actually want someone in the class to try that and then compare it to the way I'm going to do it and then tell me why one way is better than the other. I think I'll leave that as an open question. You can do it by making your variable from B to C. I just don't recommend it. All right, so my variable is L, okay? And whatever I make L, and you can, first of all, let's think about the domain of L. So let's start with the variable is going to be L, and what does L mean? Which means the distance along the shore not covered by the cable. So in other words, from point A up until point C. So the length from point A to point C. So this is I'm not actually running any cable along this L, right? So that's my variable. The domain of L, okay, so the domain is 0 is less than or equal to L, which is less than or equal to 12. Now again, let's think about why this is for a second. If I make L 0, basically what I'm saying is I'm going to run the cable all the way from B to A and then straight across. If I make AL a negative number, right, then I've run the cable like too far. It really doesn't make sense to run it that far, right? If I run, sorry, I'm not sure why my point C got kind of locked here. Okay, let's use a slider. Just make this easier. So it can be any number from 0 to 12. And I'm going to make point C defined as 0L. Okay, so let's just to visualize this one more time. I can make L as low as 0. If I make it negative, I can do it physically makes sense. It just doesn't make sense in this question because my power line would be running past the point, like I'd be just adding extra cost for no reason. Similarly, if I make L beyond 12, it's just adding extra cost for no reason. So L can be any number between 0 and 12, right, is what we're looking at here. Now, the equation, the distance to optimize, let's represent, so ultimately I'm trying to optimize the cost, right? Before I get to the cost though, I need to find some equations for the distance. So equation for distance. Okay, D1 we're going to say is the distance on land. D1 is really easy to find. D1 is simply equal to 12 minus L, right? Because if let's make L 2, for example. Then the distance along land is going to be 10, right? If this is a 2, then this is a 10 to get from B to C, right? That which would be my power segment F. So the power segment here, sorry. Okay, can't do it that way. Sorry, so segment F, we're just going to get the name, so name and value. So this is what I call, I just renamed this one, so let's rename it to D1. Okay, so that's the distance along the land, and it's all that I have to do to find it is just take whatever my L is and subtract it away from 12. So again, if my L is 3, then my distance along land is 9, right? So that's 12 minus L, very straightforward. Now D2, okay, is the distance on water. Now, this is a little bit harder to find. You need to remember, how do you get the distance between 2 points, right? The distance between 2 points, you're going to use your Pythagorean theorem in order to solve. Let's just zoom in on this for a sec. On one side, I have L. On the other side, I have 4. And then I had the hypotenuse is the distance. So D2, right, what I know is that D2 squared is equal to 4 squared plus L squared, right? That I know that because, again, L is this vertical height, 4 is the distance away in the water, and the from C to L, which is the distance I'm looking for, right? Remember that's G here, is the hypotenuse. So right now the hypotenuse is exactly 5, right? Because, and again, I'm going to rename this to D2. Okay, so there's D2. It has a distance of 5. And you can see that, if this height is 3 and this length along the bottom is 4, then the hypotenuse would be 5. Okay? Now, to isolate D2, we get the square root, and I'm only going to take the positive square root because, of course, D2 has to be a positive number. It can't be a negative, so I'm not taking the negative square root. And it's equal to square root 4 squared plus L squared. Okay, so the total distance, okay, is equal to 12 minus L plus square root 16 plus L squared. Okay, that's going to be my equation for the distance. Now, if all I needed to do in the question was minimize the distance, then what I would do is I would take the derivative of this, I would, find out when it's 0, get the absolute min, and I'd be finished. But I'm not actually looking for a distance in this question. Remember, I'm trying to optimize cost. So what I'm going to do is I'm going to do $2,000 times the distance along the shore, 2,000 D1 plus 6,000 D2, right? And again, where is this coming from? The cost is equal to whatever distance you're going along land times 2,000 and whatever distance you're going along water times 6,000. So that's where I get 2,000 D1 plus 6,000 D2. So let's write a cost equation that only uses L as a variable. 2,000, okay, 12 minus L, plus 6,000, and then square root, let's just copy paste this. Okay, and that's my cost equation, and that's all I need to minimize in order to get the answer. Again, this is a closed interval, so I should compare C0 versus C12 versus C of any critical point, right? That's the same thing that we were doing in the past whenever we saw a closed interval. So let's quickly calculate C0. Okay, so C0, so C0, remember, would be what if I ran the cost all the way down to the bottom here? How much would that cost? So let's write the cost equation again. So I said it was 2,000, 12 minus x, and then plus 6,000 square root 16 plus x squared. Okay, that's going to be my... Oh, I see. I don't think I can rename it. So let's just call it cost. CF for cost function. Okay, so there's my cost function. If I type in 0 into my cost function, it tells me... oh, sorry, not CF of 0. Actually, it's undefined. That doesn't seem possible. Oh, I see. It's a point. I see. Okay, sorry. CF of 0, it's going to cost 48,000. Okay, so 48,000. If I run the cable, that should make sense, right? Because it's 12 kilometers along the ground, so that's 24 grand. And then it's 4 kilometers in the water, which is another 24 grand, and so it costs 48 grand altogether. CF of 12 would be, what if I just run it all the way through the water completely? Right? So what if I just let it run through the water completely? What I would do there is I would take 12 squared plus 4 squared and then square root it. That would be your distance. It's a 12.65. You multiply that by 6,000 because it's all in the water, and you find that the cost of running it there would be 75,894. So running it all the way through the water is not a good option. It's much more expensive. Because I have two endpoints, maybe my answer is 0, or maybe my answer is a critical point, right? So let's say C of 12 equals, or approximately whatever, what was it, 76,000, whatever, right? Well, okay, fine, I'll write the answer, I guess. 7589466. Okay, so obviously C12 is not the answer. C of 0 might be the answer, but what I need to do before I do that is check the critical point. So let's find C prime of L. C prime of L, okay, is going to be 2,000, okay, 12 minus L to the 1. You drop it down to the 0, right? Okay, and then you multiply by the derivative of the bracket, which is a -1, right? So I'm just imagining if I had a 1 in the top corner, the 1 comes down in front, the bracket drops to a 0, and then I take the derivative inside the bracket, okay? And then the other side, I'm just going to write this a little bit differently. It's 6,016 plus L squared to the power of 1/2, right? And so what do we do there? The 1/2 comes in the front to change the 6,000 to a 3,000. The 1/2 then drops from positive 1/2 to negative 1/2. And then I take the derivative of inside the bracket, which is 2L, right? Because the 16, the derivative would be 0. So let's clean up this derivative a little bit. C prime of L is equal to negative 2,000, right? Because 12 minus L to the power of 0 all just turns into 1. And then I have plus 6,000 L divided by 16 plus L squared square rooted. So let's just we can put the root sign back, I think, now. Okay, that is my derivative. Okay, so there's your derivative. Now, if you can find a critical point that's equal to 0 in the interval we're looking for, then that could be a candidate for the absolute min, right? So c prime of 0, we're going to replace it with 0 equals negative 2000 plus this chunk. So let's solve this. To solve this, I'm going to put the 2000 on the other side, and I'm going to multiply the square root 16 plus L squared to the other side, and this is equal to 6000 L. Okay, so you see what I've done there. Then I'm going to divide both sides by 2000, so I get, just copy the same thing. So if I divide this side by 2000, I'm left with 16 plus L squared. If I divide this side by 2000, I'm left with 3L. Now what I'm going to do is I'm going to square both sides, so I get 16 plus L squared equals 9L squared, and therefore 16 equals 8L squared, and therefore 2 equals L squared, and plus or minus root 2 equals L. I'm going to reject negative square root 2. So I come to the answer that L is equal to L is equal to the square root of 2. That is the ideal according to my work here. So I go back to do my original function, my cost function. We're plugging in root 2. Okay, and if I do that, so let's make L equal to square root 2. If I do that, my cost, so CF of square root 2, is 46,627.42. So it's for 46627. Which you can see is slightly lower than the other options, right? So it's lower than 48,000. So let's write again. C of root 2 is less than C of 0, which is less than C of 12. Therefore, C of root 2 is the absolute min. So is the absolute minimum cost. Let me just quickly check and make sure I did all that right, just so we get the right answer here. So let's take the derivative of CF. Okay, so it's this. Let's simplify, and then let's find its root. So root CF prime between 0 and 12, and it comes up with this answer at 1.41, which is x of e squared is the number 2. So it's the square root of 2, right? So that's the ideal spot. Now again, the function that it drew, let's just look at the function that it drew for a sec. The cost is really, really, really high because, so there's the derivative. Okay. The cost function itself is even much higher than that. So there's the cost function in brown. Stretch it out a little bit. And you can see that it has a minimum. It has an absolute minimum right there. Right? Let's go. So we'll write minimum CF between 0 and 12. It locates a minimum at root 2 and 46,627.42 cents. Right? So that's the ideal spot to draw. So if I draw CF here, let's draw CF over 1,000, so we can we can compress it so we can actually see it on the scale that we're working with. Right, so let's just show one more time. Sorry. Okay, so let's go back and hide the equations for a sec and get the rounding back to normal. So let's hide the cost and the derivative and the point E. At this specific point, right, you reach the best possible scenario of how much you should go along the C, or along the sea, and how much along the land. So what is the question actually asking us? Find the location of point C on the shoreline where the power cable should enter the water. So we say the location, if A is located at 0, 0, and B is located at 0, 12, C should be located at 0 and 1.41, or square root of 2. Or in other words, C is square root 2 kilometers north of point A. Okay, and that would be our answer. So really, really good question. There is a question like this on the assignment you can practice. It's very similar to the question you might expect on the test. So give it a try. I'm going to leave question 2 for you. I'll open up a discussion post where you can try it. But I think it would be interesting if people tried it with different values here for the number 2. Like, it doesn't have to be 3 times as expensive. Maybe it could be 4 times expensive, or 2 times as expensive, or 1.5 times as expensive, or whatever, and just play around with it and experiment. But anyway, I'm going to leave that one for you. I've shown you the method. You should be able to do it now. It'll be a good test to see if you understand. Okay, now the other type of question we get is this kind of question with the trains. So it says, train A leaves the station at 10 p.m. and travels south at 60 kilometers an hour. Train B has been heading west at 45 kilometers an hour and reaches the station at 11 p.m. At what time were the 2 trains closest together? Okay, so I'm going to save this. I'll let you just quickly... fix this quickly, and then I'll upload this and share a link with it that you can use it if you want to just experiment with it. So save as, we'll just say power line question. Okay, anyway, the train question is a little bit different. Let's see what the train question looks like. So first thing I'm going to do is I'm going to create a slider called T. It's going to be anywhere between 0 and 60, because I'm going to say it's 60 minutes. Okay, between actually let's keep it in hours. I'm just realizing that probably makes more sense. Sorry. Let's make a slider T between 0 and, let's say, 2 hours, and let's say we count up by 1 over 60, so we count it up in minutes. Okay, so here it is. Every tick will be a minute, right? So we get up to 1 will be 60 ticks, and so on. All right. Now it says that train A leaves the station at 10 p.m. and travels due south at a speed of 60. So let's make a quick text here. So the current time is going to be T 60 10. Oh, I see. Okay, so there is the current time. So 10:55. Okay, so the time, so every tick is going to change the time by 1 minute, and then right. Sorry, T over. Sorry, floor T is all we need there, and then we need 60 T. Yeah, but that won't work. Okay, so you didn't need to watch me figure that out, but I think this now correctly deals with the time. So 10 o'clock all the way up to 11 o'clock, and then to 12. Okay, so it's 10 o'clock, right? And it says that the train A leaves the station and travels due south at 60. So what I'm going to do is I'm going to make a point called A. It's going to be located at A and negative 60 T. Okay, so let's zoom out. And there's train A, and you can see it's just heading steadily away. So here it is, heading steadily away at 60 kilometers an hour, because here we go, at exactly 1 hour it's traveled 60, and at 2 hours it's traveled another 60, right? So there it is, there's train A. Okay. Now, it says train B is heading due west, and it reaches the station at 11 p.m. So that means at 11 p.m., right, train B is at the station. So B would be located at 00, but only at 11 p.m., right? Where would train B have been an hour before that, at 10 p.m.? It says it's traveling due west at 45 kilometers an hour. So point B, right, would start at the point 45, and it would be moving left at 45 kilometers per hour. So I'm going to say 45 minus 45t. Now what does that mean? That means at t0, right, here's train B located at point 45. After 1 hour, train B is at the station, and train A is 60 kilometers away south, right? Obviously, after 1 hour, the trains are going to get farther away because neither one of them is getting closer to each other anymore, right? Like B is going west away from A, and A is going south away from B. So you don't actually really need to worry too much about what's going on in the question after 1 hour. But anyway, the distance between the two trains, let's make a segment. So segment BA, and that's going to be the distance between the two trains. So at 10 o'clock, right, the distance is 45 kilometers. At 10:10, the distance is only 38 kilometers. But you also know the distance at an hour, right, is going to be 60. So the distance at the beginning is 45, and it starts dropping until about here, somewhere around here, right? And then it starts to rise. Okay, and obviously once it's past this point, it just keeps rising, and it doesn't get closer again. So the closest the two trains ever were together is somewhere in this neighborhood around, half an hour or so, abouts. Again, let's track their distance with an equation. So let's say 10t and f, length f. Okay, so this is going to track the distance between the two trains, okay? So at the beginning, the distance is 45, it drops, 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 and then it starts to rise, and it never comes back, right? It just keeps rising after that moment. So you can see, the distance that we're going to need here. Let's just spread it, just let it stretch out a bit. Okay? Something like, in this neighborhood, it reaches its minimum. Let's shade this out to 50. Make this a little easier to see. Sorry, went the wrong way there. Okay, so there we go. So we're looking for something like in this area, the two trains are as close as possible together. To solve this question, we need to create an equation that represents the distance between the two trains, right? So in other words, it represents this distance here, d. Now this distance d is the hypotenuse of a right triangle. So what we need is an expression that goes from 0 to b and an expression that goes from 0 to a, and that will tell us the two things we need for d. Okay, so d in this question. So let's start with d squared. Okay, now where's train A? Train A, which is the height of the thing, is just located at 60t, right? So like if this, so let's do it this way. So segment OA. Okay, that little segment F is going to be equal to 60 times t, because that's how fast, the train is. Look at F and look at the segment, right? F is the exact distance, 60t, because the train started at 0 and is traveling at a speed of 60 kilometers per hour, right? So that's one segment. Now the other segment's a little trickier. It starts off as 45, but it's actually shrinking at 45t, so let's do the same thing. So let's create a segment from O to B. And then let's do the equation 45 minus 45t. And if you look at these two numbers, g and a, you'll notice that they are the exact same, right? That segment, g, is just equal to 45 minus 45t. Okay? Again, you should really think about why, right? As the train moves, that distance is started out as 45, but it's going to shrink. Now, the equation we need, right, would be the square root of 60 squared, 60x squared plus 45 minus 45x squared, right? That's going to be the distance that we need. We're just going to need to minimize it. Okay? If you horizontally expand this for a sec, maybe not that much, right? You can see if I horizontally expand it a little bit, you can see where I'm looking for a minimum. Okay, now let's think about this the same way. The domain is a closed domain. D 0 is less than or equal to t. Sorry, I'm not doing the domain. The time is the variable I'm looking at. Now, why is this true? Before 1 hour, train A wasn't moving, so they couldn't possibly be before 1 hour because train B was just farther away. Sorry, not before 1 hour. I'm sorry, before 0 hour. Okay, after 1 hour, train A is moving away from train B, more south, and train B is moving away from train A, more west. So it cannot possibly be after 1 hour. So our only options here are between 0 and between 1. Now we know that D of 0 is 45. We know that D of 1 hour is 60, because at 1 hour train B is at the station, but train A is 60 kilometers south of the station. So D of 0 is 45, D of 1 is 60, and D of some critical point could be a smaller distance. That's what we need to find out. So let's find the equation. D of t is equal to 3600 t squared. I'm going to expand. Well, I guess you don't need to. 60t squared. Sorry. Okay. Square root 60t squared plus 45 minus 45t squared. Okay, that's the function that we need to find the absolute minimum of. So we go d prime equals. How do you do the derivative here? You're going to start by bring the 1/2 to the front, copy the bracket out exactly as it was, and then to the power of negative 1/2. Okay, so you have that. Okay, then you have the derivative of what's inside. Now the derivative of the inside here, okay, would be 2 bracket 60t to the power of 1, right? And then times the derivative of the inside, which is a 60. Okay, then we keep going with the derivative. 2 bracket 45 minus 45t, drop it down to a 1, and multiply by negative 45. Okay? So again, just to walk through that for a second, this 2 comes to the front, then I copy out the 60t and drop it to a 1, and then I take the derivative of the inside, which is a 60. Then I look over here, bring the 2 to the front, copy it out, drop it to a 1, take the derivative of the inside, which is a negative 45. Let's write this in a cleaner way. Okay, so we're going to get, this is in the denominator. Sorry, I don't need a negative 1/2 there, because just a negative 1 is, because I already have the square root. So, okay, so just to clean this up a little bit, let's write what we know. The numerator has a 1, then it has this big bracket. So 60 times 60 is 3600 times 2 is 7200t. Then we have minus 90, 45 minus 45t. And on the bottom, we have a 2, and then we have this root. Okay, and that's our derivative. Now again, we can clean up the top a little bit more. So let's go ahead and do that. 90 times 45 is 4050. And then we have plus 4050t. Okay, and obviously I can get rid of the 1 because 1 doesn't do anything. And now I can get rid of the brackets. And I can make this a little bit cleaner if I just combine these two terms together. So 7 and 4 makes 11. Then I keep the 2, and then I put the 5 there. And I get that. Now, that was complicated enough that I feel as though I should check on GeoGebra and make sure I did this right. So let's rename this function to d, and then we'll take the derivative. And I definitely didn't do it right, so where's the error? Maybe I'll pause this while I look for the error. Okay, I think actually it wasn't a mistake. I just typed it into GeoGebra wrong. I didn't square the 60, I just squared the x. So I think we're actually right here. So let's keep going anyway. We'll see if we get an answer. So 0, okay, so we know the critical point is when d prime is 0. And here's the beauty of these questions, because all that ugly stuff on the bottom, we can just ignore it, right? As long as we get an answer that's inside the domain, right? And you can see here, the domain actually isn't really going to be a problem because it's something squared plus something squared. It's always going to be positive. So the bottom, just take the bottom and multiply to the other side, right? So take the bottom, multiply to the other side with the 0. And what happens is you're only dealing with the top, right? So then you get 4050 equals 1125t. 4050 divided by 11250 equals t. And I think that, let's just see what that reduces to quickly. So that's 4050 over 11250. And that reduces to 0.36. Let's see if we can get that. Yeah, 0.36 exactly. Okay, so t equals 0.36. So 0.36 hours after 10 p.m., the trains will be as close as possible. Now 0.36 hours, you could turn that into minutes by multiplying it by 60, right? You get 21.6 minutes after. So again, you could turn it into seconds if you wanted to, I suppose. But so 10, 21, and 36 seconds is when the train's together. Okay, so at what time were the trains closest together? So that's what we had to do. Let's test that. So here's my theory is that t should be t should be 0.36. So let's look at t as 0.36. I don't need this many decimals. Okay. Okay, so you can see it's something like here where the distance is reaching its smallest possible value. Let's look closely at the distance. So again, here's the distance over here, d1. As we get, so you can see, as I get closer, my distance number is dropping, dropping, and then it's rising again. So it's dropping, and then rising. So let's go right to 0.36. And there your distance is exactly 36 kilometers apart. If I go a little bit to the right, it's higher. If I go a little bit to the left, it's higher. So that's my perfect spot, right? 0.36. Now again, to turn that into a time, multiply it by 60. That'll tell you how many minutes. Then you multiply the decimal part by 60, and that'll tell you how many seconds. Right? So we get 21 minutes and 36 seconds is when they are exactly closest together. That's the minimum distance. So again, really good questions to try. I'm going to open your assignment on this topic right now, and I'm also going to post a discussion area where you can attempt this Lighthouse one here. Really good ones to give it a try and see if you understand them. I think these ones are pretty high on the difficulty scale. It doesn't, after this we're doing an economics section. And after that, I think we are actually finished because we're not going to do the supplement. So one more lesson on economics, and that's it for this unit. So give this Lighthouse Untrained question a try and post any questions to the discussion area.